scenario with the readings of speedometer like 50 km per hour, 70 km per hour, where the speed is changing continuously during time. The speed your speedometer displays at each instant of your travel is actually an important element of calculus. That is limit. This section is designed to help us understand what limits are and its basic fundamentals. So first, we can illustrate one-sided limits by an example. Consider the function f of x is equal to 2 for x less than or equal to 0, f of x is equal to 3 for x greater than 0. Check the existence of the limit of function at x is equal to 0. The graph of this function is given here. It is clear that the value of the function with x less than or equal to 0 equals to 2. So the left hand limit of f of x at 0 is limit x tends to 0 minus f of x is equal to 2. Similarly, the value of a function f at 0 with x greater than 0 equals 3. So that is limit x tends to 0 plus x f of x is equal to 3. In this case, the left hand and the right hand limits are different. Hence, we can say that the limit of the function as x tends to 0 does not exist even though the function is defined at 0. So, from the given example, we got an idea that there are essentially two ways x could approach a number a, either from left or from right. That is, all the values of x near a could be less than a or could be greater than a. This will lead to two limits. One is left hand limit and the other is right hand limit. Right hand limit of a function f is the value of f of x when x approaches a from the right, and it is denoted by limit x tends to a plus f of x is equal to L. Similarly, the left hand limit of a function f is the value of f of x when x approaches a from the left. That is, limit x tends to a minus f of x is equal to L. Now, we can interpret the definition of limit by an example. Consider the function f of x is equal to x cube. Here we can observe as x takes values close to 0, then the value of f of x also move towards 0. We say limit of f of x as x tends to 0 equals to 0. So, in general, as x tends to a, value of f of x tends to L. Then, L is called the limit of the function f of x. Alright. Now, and its representation is given by limit x tends to a, f of x is equal to L, and where this L is called the limit. Here is another illustration for the existence of limit. Consider the function f of x is equal to 3x. Let us try to find the limit of this function at x is equal to 2. Let's see the table. This table shows us the value of x and its corresponding f of x values. When we calculate limit x tends to 2, f of x, we get it as 6. Just see the previous slide. From table, we can also observe that x approaches 2 either from left or right. The value of f of s seems to approach 6, as you can see from this table. So, limit x tends to 2 minus f of x is equal to limit x tends to 2 plus f of x, which is equal to limit x tends to 2, f of x is equal to 6. So, hence, here in this case, left hand limit equals the right hand limit. So, the limit of function f of x exists. We all know what is algebra, and in algebra, there involves many arithmetic operations like addition, subtraction, multiplication and division. Here we have formalized the algebra of limits as a theorem without proof. Let us take one by one. First, we can discuss the addition. Take two functions f and g such that both the limits of function f and function g exist as s tends to a, then limit of sum of two functions is the sum of the limits of the function. That is, limit x tends to a f of x plus limit x tends to a g of x. Next, we will discuss about the subtraction of two functions. Here also, we can take two functions f and g such that both the limits of the function and the function g exist as x tends to a. Then, limit x tends to a f of x minus g of x will be limit x tends to a f of x minus limit x tends to a g of x. Now, we can describe how the product of two functions are carried out. The limit of product of two function is the product of the limits of the function. That is, limit of f of x into limit of g of x. So now, next we have the quotient of two functions. Limit of quotient of two functions is the quotient of the limits of the function. That is, limit x tends to a f of x by limit x tends to a g of x. Now, let's see a special case of product. When g is the constant function such that g of x is equal to c, where c is some real number, then we have limit x tends to a, c into f of x is equal to, c is a constant, so we can take it outside. So, this will become c into limit x tends to a f of x. In this section, we illustrate how to utilize this theorem to evaluate special types of function, that is, limits of polynomials. A function f is said to be a polynomial function if f of x is equal to a0 plus a1x plus a2x square up to an x raised to n, where ai's are the real numbers such that n is not equal to 0 or for some natural number n. As we know, limit x tends to a, x is equal to a. Hence, the limit x tends to a, x square will be equal to what? A square, using the product of two function. And by this way, we can generalize, that is, limit for x raised to n will be equal to a raised to 2n. Now, consider f of x is equal to a0 plus a1x plus a2x square up to an x raised to n be a polynomial function. Consider each term as a function. Then we have limit of f of x as x tends to a is equal to applying the limit here on the RHS. So, we get limit x tends to a, the RHS. Now, here we have to apply the limit of sum of functions. Then we will get separate limit. Limit x tends to a0 plus limit x tends to a1x, so on. So, within this limit, again we have to apply the limit of product of function, because here a1 into x, a2 into x square. So, after applying, we get it as a0 plus a1 into limit x tends to ax plus a2 into limit x tends to x square, so on. Now, what is the result over here? a0 plus a1 into a plus a2 into a square up to an into a raised to 2n. On final rearranging, we get this final result as f of a. Now, we can discuss about the limits of rational function. Now, what is a rational function? We know that a function is said to be a rational function if f of x is equal to g of x by h of x, where this g of x and h of x are polynomials. Also, the denominator, that is h of x, should not be equal to 0. Now, while applying the limit to this rational function, we get it as limit x tends to a g of x by h of x. Applying the limit separately using the quotient of for the given function, we get it as g of a by h of a. While discussing the limit of rational function, we should also know about the limit of an intermediate form. What does this mean? Limit x tends to a f of x by g of x is said to be of the form 0 by 0 if the limit of the function f as s tends to a is 0 and limit of x tends to a g of x is also equal to 0. And this is called actually indeterminate or 0 by 0 form. Let's see one question. Compute limit x tends to 2 x square minus 3x plus 2 divided by x minus 2. Let's see the solution. Here the limit is of the form 0 by 0. If we assume x is not equal to 2, then we can write it as x square minus 3x plus 2, we can write it as x minus 2 into x minus 1. Now cancelling x minus 2 on the denominator and the numerator, we get it as x minus 1. So our function is equal to x minus 1 everywhere except at one point, that is x is equal to 2. So for all values of x near 2, the function is equal to x minus 1. This means that limit x tends to 2, our function x square minus 3x plus 2 by x minus 2 will be equal to limit x tends to 2 x minus 1, which is equal to, applying the value 2 minus 1, we get it as 1. So the value of the function we get here is as 1. Now look at another theorem. The theorem says that for any positive integer n, limit of x raised to n minus a raised to n by x minus a as x tends to a will be equal to n into a raised to n minus 1. To prove this, we have x raised to n minus a raised to n can be written as x minus a into x raised to n minus 1 plus x raised to n minus 2 into a, so on up to a raised to n minus 1. Now divide this by x minus a. So we get it as limit x tends to a, x raised to n minus a raised to n by x minus a will be, applying the limit on the RHS, we get it as limit x tends to a, x raised to n minus 1, so on up to a raised to n minus 1. Now applying the limit inside, we get it as the answer as a raised to n minus 1 plus a into a raised to n minus 2, so on up to a raised to n minus 1. Again, this value will repeat n times. Alright, this a raised to n minus 1. So we can write it as n into a raised to n minus 1. Hence, we have proved the theorem. Now let us look at another example. The question is to evaluate the limit of x raised to 15 minus 1 by x raised to 10 minus 1 as x tends to 1. Let's see the solution. Here, we divide the numerator and the denominator by x minus 1. Then the fraction will be rearranged as in the form of above theorem. We get it as like this, that is, we apply the quotient rule and the limit. Now applying the values, we get it as 15 into 1 raised to 40 divided by 10 into 1 raised to 9. On solving, we get 15 divided by 10, which is equal to 3 by 2. So far, we have discussed the concepts of limits and they serve as the basis for the definition of the derivative, which will be discussed in the upcoming video. Now, let's wind up the section and here's a summary.
Manorama Horizon. Learning made simple.